solve for VF, the final velocity, and when you do the algebra on that, you're going to come up with that equals the square root of 2g times h. Take the square root, and so there's the equal sign, and then here, and it's all given in standard units, so meters, meters per second, meters per second squared. So you have to come up with standard units, meters per second. When you take the square root, you're coming up with two results, a positive and negative, and you have to decide which one. Well, looks like he is swinging to the right, so your result should come out to be a positive velocity to the right. Okay, in hindsight on this problem, I actually noticed that that check mark that I made here, I shouldn't have made a check mark there. We don't have this given, but instead what I should have written there is that this is actually what we're looking for. Of course, as we did the problem here, that's what I did anyway, but properly I should put the question mark there because that's what we're supposed to solve for. This one I call problem C, apparently the water skier. Okay, and it says a water skier lets go of the tow rope upon leaving the end of a jump ramp at the speed of 14.0 meters per second. As the drawing indicates, the skier has a speed of 13.0 meters per second at the highest point of the jump. Ignoring air resistance, determine the skier's height, h, above the top of the ramp at the highest point. Okay, so here, and the number's already given, so the initial velocity is 14.0 meters per second. The final velocity is 13. Ooh, that looks a little bad. VF equals 13.0 meters per second. Of course, gravity is always implied, and what they want to figure out is what the height is. Again, mass isn't given here for the water skier, so I assume that it will divide out, so I'm going to make an, cross it out here that we actually won't need it. Okay, down here we would have kinetic energy, and granted we also have potential energy above the water line. However, they don't tell us how far that is above, and again I'm going to choose a convenient zero level potential energy, and again that's going to be where he takes off here, so it's going to be potential energy equals 0 joules right there. And then at the top he will have, is it a he or a she? Actually they don't say, so oh yeah, he's bare chested, so we assume it's a he. And so up here he has a certain kinetic energy, and I might want to call this one here final kinetic energy, and this one here the initial kinetic energy, and of course he is at a higher level, so we call it the final potential energy. Okay, so towards the bottom and then towards the top, what I come up with is that I have initial kinetic energy equals the final kinetic energy plus the final potential energy. Okay, and now I'm going to write 1/2 mass velocity original squared equals 1/2 mass final velocity squared, I'm almost running out of space, plus mass times gravity times height. Of course, it doesn't matter that they use a capital H and I use a lowercase h. Okay, and as predicted, mass divides out, and we're supposed to figure out what the height h is, so that's what I'm going to do the algebra on. H equals, and that means I have to get the VF to the other side, the VF squared, so it's going to be V0 squared minus VF squared, and then I reserve that 1/2 actually, that I put that 2 in the denominator. There we go, because I have to put the gravity actually in the denominator as well. And so here you plug in 14 meters per second and square that, and here 13 meters per second and square that. Notice that when you subtract this number from that number, you come up with a positive, which is, and then you divide here by 2 and you divide by 9.8. And that's good that you come up with positive, because he goes up in height, and that should be positive as well. And when you do the unit analysis, you're going to come up with meters squared divided by seconds squared, both of these here, and then divide by meters per second squared, and overall you're going to come up with that the second squareds cancel and one of the meters cancels or divides out, and you come up with meters. So a positive height in meters. To add a little bit to this one here, if you look at the algebra here, you see a v0 squared, and if I get this back over here, I have 2gh, or 2 acceleration times distance, 2ax for example, and then I get the vf squared over there. So for example, I could make it look like this. It would actually read 2ax, again if I make the 2gh into 2ax, and then I add vf squared to that, and that equals v0 squared. And that one actually is the same that you found in the kinematic chapter, where this one is a derived equation from the others. So in the kinematic chapter on the kinematic equations, there was already an equation that goes back to the conservation of energy with the kinetic energy and potential energy. So that one here is the same as this one. This is just on top of the problem. It has nothing to do with the calculations.